Hello and welcome to my channel. Since this is the first real video that I'm going to be posting here, I figured I should introduce myself at least a little bit. So I just finished my PhD a few weeks ago, and during that process I figured out that helping people learn is something I'm really passionate about. So I decided to start this YouTube channel as a way to share all the cool projects and ideas that I've been working on with all of you guys. And the goal of this channel is to make high-level math and computer science concepts accessible to everyone. So I'm going to be making videos on anything from machine learning and computer graphics to theoretical mathematics and generative art, kind of like what you saw in the introduction. Now, the topic for this specific video, the video editor, was actually motivated from playing the trading card game Magic the Gathering. Now, if Magic isn't your thing or you don't even know what it is, that's totally fine. This video is entirely about the automated video editor that I made for Magic, so it should really work for any type of content. But I actually did get started on YouTube making gameplay videos of Magic the Gathering. If you're not familiar with Magic, you can just think of it like chess or your other favorite strategy game. And games like these, while they're very engaging to play, a lot of the interesting stuff happens in your head. So making content like this is very challenging because from the viewer's perspective, you can just end up with sequences where there's just two players sitting around across from each other doing nothing for a lot of the time. And I experienced this when I was making content where I would record games that took like 2 hours to play, but I could edit them down into like a 30-minute segment, and doing all of that manually took forever. So I built the automated video editor to do this process for me. And during the process, I realized this can work for a lot of different things. So, any type of gameplay it would work for. If you're just making and recording videos like this, for example, and want to remove gaps, it would work there too. So this is a general video editor. I'm just showing it with examples from Magic because that's what I made it for, and I think it still is a very demonstrative example of the capabilities of an editor like this. So to get us started, I'm going to show a short 30-second clip of Magic as an example. And we're going to use this to set the stage for how much we can improve the clip going forward. And I know it's going to feel painfully slow, especially to those of you who don't even play Magic or don't like strategy games, but that's exactly why I'm making this video in the first place. It might start out really rough to watch, but we get to spend the rest of this video making the clip bearable to watch, maybe even fun to watch, and hopefully learn a lot of cool stuff along the way. Here's the clip. So we can play this friend. And then hit forward 2. Target player's sacrifices an artifact. Okay, so that was probably painful to watch. That experience you had of just sitting there wanting to skip ahead in the video is caused by what we're going to call dead air. While small segments of dead air in a video can make it frustrating to watch, longer segments like the pause at the end there could just make it unbearable. So our goal going forward is to just remove all of that from happening. Now, because we're going to approach this problem scientifically, the first step we need to do is to quantify what exactly we mean when we say dead air. It might be obvious to us when we see it, right? You can just go back to that clip and say, all of this was bad. But because we're trying to create an automated video editor, we need a quantifiable set of conditions that need to be met so we can tell our computer how to remove it. And to do that, we can start by looking at what information a typical video has in it. Typically, you're going to have one channel for audio and one channel for video. While both of these are going to be running continuously, some parts are just going to be less exciting than others. So for example, you can have audio where there's nothing but background noise or a frozen video. And I'm going to use these boxes to represent each of these channels in sort of a binary representation. Either something interesting is happening or it isn't. Now, on their own, each of these channels doesn't tell us whether there's dead air or not. What we need to do is consider them both together and how they're working. For example, you can have a podcast where there's no video, but it's still totally entertaining. And there's a lot of silent movies or visuals that can be fun to look at, but a silent podcast, when you consider both of them together, is just not a thing. So since we're using a binary representation on our audio and video channels, we get to use fancy logical operators like this NOR operator. And it might seem fancy, but one goal with this channel is to kind of slowly introduce you to mathological terms if you're not used to them. And what NOR means is simply to look for times where both channels are off. So in this case, it would be where there's no audio or video playing. It actually comes from the English word nor, or if you were going to say like neither audio nor video. And visually, we can do this by overlaying our two channels and just looking for gaps. So these purple regions are the regions where the NOR operator on the audio and video is true, or basically where there's no audio or video playing. So going forward, this is what I'm going to mean when I'm talking about dead air. So our goal with the editor then is to remove all the regions of the video where there is no audio or video signal happening. So you can basically think of it as you're using the NOR operator on our audio and video channels. The next step we need to do is figure out how we define these on and off binary representation for our audio and video channels. We'll start by looking at the audio channel because it's a lot more obvious in this case. So here I'm plotting the amplitude of the sound waves entering the microphone, or basically just the audio volume. And what you can see is that it never really gets down to zero. There's some background noise either in my microphone, my recording room, or loud neighbors that's going to provide you a continuous baseline level. So to overcome this, we can establish a threshold value. And by this, I'm drawing these white lines. Essentially, we're saying that anything quieter than this white line is off, or we don't care about it, so we can remove it, which I'm doing here. So now you can see my audio packets kind of look like they're floating, and we're getting very close to the binary representation I showed before. The most obvious way to make it even more clear is rather than drawing the waveform packets, we introduce another threshold value, and basically saying anything above this white line is just constant. It means it's just continuously on. So we draw them as boxes here. And so now when we remove the boxes, when I talk, the audio signal is on, and then when I'm pausing, the audio signal is off. So we've kind of got there, right? But there's actually more audio information we can use than just looking at the total volume. We get an entire spectrum of sound to work with. So the visualization I'm showing here is a plot of the audio spectrum and how it's changing over time. The y-axis is representing pitch, so the lower sounding bass frequencies show up at the bottom, and then the high frequencies show up at the top. Each frame, I'm taking the assortment of frequencies entering the microphone and plotting them as a line on the right side. And then I'm going to shift everything to the left and repeat this process frame after frame so you get this really cool flowing sound type of effect. Now, the whole reason I'm showing this is to demonstrate that we can actually differentiate between types of sounds by looking at the audio spectrum. For example, my voice when I'm talking looks a certain way, but if I do something like whistling, I'm not good at whistling, but you can see that it's closer to a distinct peak than when I'm just talking. And if we had used the method I discussed previously with the volume thresholding, they might have similar volume, but their pitch or their sound is entirely different. And the same thing's true for something like clapping or bumping into the table. Each of these sounds is creating a unique combination of frequencies, and that's why to us they all sound different. The reason I'm showing this though is we can use this information to our benefit by, rather than just looking for times when the audio is loud, we can do things like look for a frequency pattern that matches something we're looking for. So an example would be, let's say you're playing a video game and there's a lot of background music and sound effects, but you just want to look for times when you're laughing to make a compilation of your laugh. What you can do is measure the spectrum of your laugh, or the average spectrum, right? Get a bunch of recordings so you know when I laugh it sounds kind of like this. And then go through the video and look for a sequence that closely matches the spectrum of your laughter. I mean, we as humans do this all the time. You can recognize a human voice. So it makes sense that you could train a computer to do the same thing. Unfortunately, the specifics of how you would do this is a little bit too complex to fit into what I can only imagine is an already long and complex video. So I'm going to have to talk about this more in a future video. I just wanted to introduce this to show you that, even if I show a lot of cool concepts, there's so much more stuff you can add to improve your editor. And this is true for all of life. Just because I show you something, that doesn't mean it's the only way to do it. There's probably even more ways to do it than what I'm showing here. So going forward in this discussion, we're just going to be using the simple audio thresholding that I talked about in the previous animation. But as a hint for what's coming, one way you could do this is with a convolutional neural network on the audio spectrum. And speaking of what's coming next, my plan for this channel is to make videos explaining how every single animation I show is done. So if you want to be able to make your own interactive spectrogram and play with it for hours like I did, this is running in a JavaScript browser, by the way. I'm going to be making a coding video on how this will be done very soon. Otherwise, we'll get back to the video. Alright, so now we have an idea of how to get a binary representation of our audio signal, so we can start talking about the video next. And we're going to use this friendly dinosaur to help us out. Now, let's imagine we're watching a video clip where the dinosaur is moving around or something. And our goal here is to somehow take that information and convert it into similar binary chunks of on or off like we did for the audio. Now, to do this, we can note that videos are essentially just a sequence of images taking place one after another. So 2 subsequent frames of a video might look something like this. And for the sake of demonstration, let's say maybe the dinosaur in the second frame is moved slightly down into the right since the last picture was taken. So given this representation, the easiest way for us to determine if something is happening is to just look at the actual difference between the 2 frames. And to do that, we literally just take all the pixel values of the second image and subtract them from the first image. And it gives us something that looks like this. Anywhere that there was no change between the frames is going to show up as black because 0 looks black on a picture. And we see an interesting thing here where even though we can get a rough idea of where things are changing, we can see in the 2 regions where the dinosaur sort of overlaps itself, it's counted as not changing. We'll talk about that more in a second. But I want to demonstrate this on a live video. So I'm going to be using this awesome video of pizza that I found in the stock footage library to demonstrate these effects. So try to pay attention to the changes in this video, how it's moving and where things are happening, so you can get appreciation for what happens when we switch to the frame difference method. I'll show it maybe just the beginning one more time. And now here's the raw frame-by-frame subtraction of the video. And it works okay. When stuff is moving, we do get a signal response. We can tell that a hand shows up, we can see the pizza get picked up, and then like a slowly sliding back. But it's mostly just showing the outlines of the motion. Most of the frame is black. And this is similar to the problem where the dinosaur overlap was red as no change. If an object of a certain color is moving, you're really only going to get an outline of that motion. So while this method is very effective and really quick to calculate, there is a better method. I will say for simple tasks, this is probably all you need. And it is what I use for my current video editor of Magic. But it's worth talking about improvements again, just to give you ideas of different ways and different cool ways to do stuff. So we'll talk about that next. We can use our 2 dinosaur friends again to represent 2 adjacent frames. And again, we're going to offset one slightly as we did before. But this time, rather than calculating the actual frame by frame difference by subtracting pixels from each other, our goal is to try and find where each pixel moved between frames. This process is called optical flow. So here we're looking for the flow direction from where each pixel moved from frame 1 to frame 2. While the specifics of this algorithm are a bit too complicated to discuss in this video, I'll be making a couple follow-up videos, one showing how easily you can actually implement this using something like OpenCV and Python, and that's how I made the animation I'm going to show in a second. I'll also put a couple videos in the description just to show what optical flow is in more depth. But all you need to know here is we're trying to estimate how the frames moved between frame 1 and 2. So you'll get an outline of the original frame, and then each pixel value that moved rather than just getting a color difference, you're actually going to calculate a vector pointing in the direction of motion. Now, this isn't the easiest thing to visualize. You get all these arrows, and if you're drawing one per pixel, they'll overlap and get kind of muddied. So to make this a bit easier to look at, we can use a clever encoding trick, where we take the angle of each vector, and then find the corresponding angle on the color wheel. And then, rather than drawing a million vectors all over the image, we can just color the pixels according to this motion direction. So putting all this together, here's what the optical flow calculation of the pizza video looks like. And we can notice a few things. First is that the information is a lot more filled in. There's more than just outlines here, and due to the specifics of how I'm calculating it, there is a bit of outline effect. Basically, each iteration draws it in more and more, so you can iterate this more if you want to fully calculate all the motion, but usually this is good enough. The second thing to note here is that we get information of what direction everything is moving in. So if you look at the hand when it grabs the pizza, for example, when it's moving in, it's colored red and green. And then when it moves away in the opposite direction, it's more blue and purple. And this is pretty useful for locating specific movements within a panned video, like this one, for example, where pretty much everything's moving backwards, and they're all kind of blue and purple colors. But the hand and the pizza move forward. When they're moving forward, they're colored uniquely. So we could use this to isolate motion as interesting while the rest is not. Another good example would be like in a 2D platforming game, where typically the player is moving to the right and up. You can look for motion in that direction as an indicator, or really just anything you want to do. I'm just demonstrating this to kind of get you interested in the possible things you can use to automate an editor. And I think this will pick up motion in complicated videos much better than the previous frame difference algorithm would. It takes longer to calculate, so there is a cost there. And it's why I don't use it to edit my magic videos, because really not a whole lot is changing there. But in a more complicated video, something like this might just be more appropriate. Anyway, the two examples I've shown are just the tip of the iceberg of all possible methods you could use to estimate motion from a video. But regardless of whatever method you choose from these two or your own cool algorithm, there's one final step we need to do, where we've calculated our per pixel measure of motion, but we need to convert this into an absolute measure that'll allow us to transform our video signal into the binary representation we discussed earlier. Now, to do that, we're going to use this formula, and it might look a little bit ominous if you're not familiar with math, but we're going to go through it step by step. So the two brackets around the arrow essentially mean that we're taking the magnitude of our change between frames. So with optical flow, this means looking at how far each pixel moved from one frame to the next. Then this like squiggly thing with the pixels below it is a summation sign, and it just means add up all of these magnitudes for every pixel in the image. And then the bottom is you divide by the number of pixels. So we're essentially calculating an average amount of change per pixel. And this lets us compare different videos together, right? You could have a video with a lot of pixels in it, and then 100 pixels changing is very low. But if you have a very, very small video with like maybe only 100 total pixels, that'd be a lot of change. So we're getting basically a percent change here. And if you do this for every single frame, you're going to end up with a graph that looks like this, where the amount of optical change or difference between frames is varying over time. As before, what we were doing with the audio signal, we can establish a threshold value to account for noise in our measurement. You could have some like flicker, or if you're actually recording real video, you're going to get some noise there. And so we can use the same thresholding method as we did before to establish our binary signal. So now we've converted this continuous video frame method into the binary signal the same way as we did for audio. And that's all there really is to it. Awesome. So now we have a way to measure these binary audio and video signals. The last step we have to do is just find a way to represent them mathematically. Because as we mentioned at the beginning of the video, we need to quantitatively describe them so we can tell a computer how to remove it. And to do this, for now, we're just going to start by looking at one signal. And the most convenient way I could think of representing this is by looking at the start and end times of each of these blocks. So for example, the video is on from 0.1 to 0.7 seconds, and then off between 0.7 and 1.5, and so on. Now, it's a bit easier to just group these start and end times together and represent them using a vector, where the left or the 0 entry is the start and the 1 entry is the end. And then we can describe the entire video as a group of these vectors, or a list or an array depending on what coding language you're using, where each vector is again a start and end time. So mathematically, or putting this in a computer, this is our way that we quantitatively describe the binary representation of our video signal or audio signal in the computer. So now we have our way to measure our signals and a way to store the measured signals in the computer. All we have to do now is figure where the dead air happens given these signals. And we're going to get a little bit more abstract rather than talking about audio and video channels, and just solve the problem in general where you have two signals A and B, and you're looking for a third signal C, which is the NOR of A and B. Or essentially, as we talked about before, C is the regions where A and B don't show up. And so we have our mathematical descriptions of A and B as before, where they are lists of vectors of start and end times. So now, if you look at these two lists, you can work out what C would be. It would be 0.53 to 0.7, and then 1.1 to 1.3, and so on. And I'm going to do something a little interesting to make calculating C a bit easier. Rather than working with A and B, or when the signals are on, we can introduce new vectors or lists, not A and not B. So this exclamation mark is a common way to describe a logical negation. So you can see not A shows up in the places where A is not. So it'll be between 0.5 and 0.7, 1 and 1.3, 2.6, and so on. And the same for B. And so this is the similar analogy if you're working with video. This would be when the video is frozen because it's not video. Same with audio. This list describes when the audio is silent. And so rather than working with A and B, if we use not A and not B, then we can describe C as the intersection of these lists. We can describe this problem formally as given not A and not B, find C as the intersection of not A and not B. That might be a lot to parse, especially if you're not new to math, but let's just go through it step by step. So our vectors A and B, you can think of them as the audio and video signals. Not A means the times when the video is not moving, and not B means when the audio is silent. So the intersection of those two is essentially saying when the audio is silent and the video is not moving. Visually, it's pretty easy to understand what this mathematical intersection looks like by showing a Venn diagram. So it's literally the overlap of the two sets. And that term C is the dead air we were talking about before. And our goal is to find that given the two lists or sets of vectors of start and end times, not A and not B. This is actually a pretty interesting problem. And if you're curious, I encourage you to pause the video and try and figure it out on your own. It's sometimes used as like a coding interview question, and it's just a good exercise in logic. But if you're still here, we'll just keep going and I'll show you how to solve it. So I'm going to show this 3 times. The first time I'm going to show a visualization of the algorithm. Then I'm going to show an actual code example of how you would write this in software. And then I'm going to show a quick visualization again. So you hopefully between the 3 times looking at this, you can get a good idea of how this algorithm works. So here I've plotted the 2 sets, not A and not B, and I've color coded everything. And then I'm showing C in pink as what we're going to calculate. And so what we do is, not A and not B is a list. So we're going to start by looking at the first element in each list. And then we're going to do an operation where we look at the maximum value of the start points between both of these elements. And we're going to call that L. Then we're going to look at the minimum value of the endpoints. We're going to call that R. The final step is to check if L is less than R basically making sure this range is valid and putting that in C. Now we're going to call these L and R because they're just the left and right ends of the array that we're going to enter into C. And we just keep doing this. So we've done one step, then we find whichever array was farther behind between not A and not B, and we increment one along that list. So now we've moved to the next entry in that list. And we do the same thing. So we calculate L by taking the maximum value between the two starting points. Then we find R, which is the minimum value between the endpoints. And this time L is greater than R, so it is not a valid array. So we don't add it to C. And we just keep doing this. And visually, it actually makes a lot of sense why we're doing this, because if you're looking for the overlap, you're always going to be trying to find the smallest array that can hold both of them. So you're going to take the maximum of the start and the minimum of the end. It just kind of intuitively, like watching this algorithm go, it hopefully helps it make a bit more sense. And so now we're on our last array of A, and we have nowhere left to go. So we're done. We've calculated C, and visually you can see it lines up. We found the intersection of the two sets. Now we can move on to the code example. So I'm going to do this in Python because I figured it was the most user-friendly coding language I can think of. And it's also the language I actually implemented this in, so it just made sense. And here we're looking at the function that I've just labeled find intersection, which takes in two elements, A and B. And these are the lists of start and endpoints that we've been showing before. So the first step is just to initialize everything. So the I and J terms, these are the indices that we're going to use to keep track of which element in the lists, A and B, we are in. So we're going to start by just initializing them to 0. You can think of this like the first element if you're not used to 0-based indexing. Then M and N are the length of both of the arrays. Essentially, this is just telling us how many of these start and end pairs we need to look through. And then lastly, we initialize our cuts array. This is essentially just C that we showed in the previous slide, but cuts is kind of more intuitive because it is a list of things we're going to cut out of the video. And we start with it just as an empty array. Then we need to iterate through both lists. So this line is basically just saying while I is less than M, essentially while there's still things left to look through, keep going. And then the first thing we do is the same as before. We find the L and R bounds of our range. So L is the maximum value of the start points between the two entries in the list we're looking at. R is the minimum value of the two endpoints of the entries in the list we're looking at. And so once we find L and R, all we do is make sure the range is valid by ensuring that L is less than R. If it is, we create a new array of, or I guess vector, enclosing L and R, and we append it to the cuts array. So now we've added a new vector to the list. And that's essentially all there is. The last step is to find which of the two ranges is farther behind and move to the next element in the list. And this is what gives us this progression or that crawling behavior I showed before, and what I'm going to show now, because that's all the code. It's actually very simple. So just to walk through this visually one more time, we have not A, not B, and C. We look at the first element in both lists. We calculate L as the maximum value of the start points, R as the minimum value of the endpoints, and just add that to see if L is less than R. And we can just kind of keep going through piece by piece and finding the overlap between these two. It really does look cool to watch it go. And now we've run out of the array, so this is the last entry, and then we're done. That's all there is to it. Okay, so we're almost there. We've now calculated our audio and video signal, and the location of the cuts we want to remove, which I'm showing in purple. The last step we have to do is feed these cuts into whatever editing software we would like. I used FFmpeg, and there will be some links in the description for that. But we just need to now have the editor remove these bits from both the audio and video. So the resulting video is shorter and has none of the gaps. So visually, we can look at this. Removing the first bit of dead air would look something like this, where we cut that bit out from both the audio and video and then shift it over. We do this again for the second bit we'd like to remove, and then for the third. Great, and that's all there is to it. So we're done, right? We get to see what the video looks like now. It's a lot shorter, so I'm going to show it a couple times in contrast to the 30-second clip I had before. So we can play this frame and then hit forward to target player's sacrifices an artifact. So we can play this frame and then hit forward to target player's sacrifices an artifact. So, that was a little bit too fast. What happened? Well, the problem is that we removed all of the gaps between the clips. Normal conversation isn't like this. I pause between my words and sentences when I'm talking, but the editor that we currently have doesn't do that. It removes literally all of the gaps, and this makes the edits really jarring to watch, because it's like I'm never taking a breath. So what we need to do is instead pad our cuts by just a little bit, so the editing blends in seamlessly with the natural pauses of conversation. Okay, so what I'm showing here is a bit of a complicated scene to explain, so bear with me and it'll make sense in a second. The blue boxes I'm showing are the familiar audio signals I showed before. They show up when I talk. These new orange bars are a histogram, and essentially what they're doing is count how long each pause I take and put it into a bin. So in this case, each of these bins is one animation frame. So the farthest left bin is a pause length of 1 frame. The second is 2, and so on. So if I take a longer pause, when I talk again, you can see a spike towards the right of the histogram. And the purpose of this is to understand what my normal speech patterns are, so I can imitate it with my spacing in the editing software. Now, I know that I can never get a reasonable measure of my speech patterns in such a short time if I demonstrate them live, so I'm just going to transition to a more demonstrative example of what it would look like if I did it long enough. I just wanted to show this as an example of how you would calculate a histogram if you were going to do it. Alright, this graph should look a lot better, and it's more representative of what types of distributions I saw when I looked at the data for like hours and hours of my speech, because I had recorded tons of magic videos, so I could just conglomerate them all and look at the pause duration for all of them. And looking at that, we notice a couple things. First, there's a giant peak on the left, and this corresponds to the average pause or spacing between my letters and words. Because these are much shorter and there's way more of them, they're going to completely dominate the distribution, but I'm not going to be making many cuts mid-word, so it's pretty reasonable to ignore this peak for now. What we're interested in is this secondary peak. This corresponds to the timescale between sentences where I finished one thought and I'm waiting for another to show up. And if we want our video to feel like a conversation, we should adjust our pauses so they're roughly this length. In my case, this value, I'll call it like P bar, was roughly half of a second. And this might seem short, but you have to realize how big of an impact a small change in this parameter would have on the final video length. For example, a 2-hour video would have thousands of potential edits in it. And if we're adding half of a second per edit, that already increases the video length by around 1,000 seconds, or that's 16 minutes of silence that we're just adding to make it feel natural. And just increasing this to 0.6 seconds instead of 0.5 would add an additional 4 or more minutes of video time. So you really do need to carefully consider what value you set this to strike a balance between having a reasonable video pace and just making it way too long. And with that, we're pretty much done. We're going to go through this graphic one last time, just so you get a clear idea of what we're doing. So we found our video and audio signals. Then we calculated the regions we wanted to remove. And now we have the one extra step we just discussed, which is to pad the measured signals by 1/2 of our average pause length between sentences. We're going to use 1/2 because the padding happens on both sides of the cut. So together they'll make for a pause of the full expected time. And with this new value, we can calculate slightly different cut values. In fact, the third cut is completely gone now. So given these new, I'll show them in pink, these new cuts, we can now edit the video. And then we'd make our second cut. And now we unpad our videos to look at the actual unpadded audio and video signals. And we've noticed that we've preserved a small gap between our cuts this time. So we're done. We finally get to see what this looks like. So remember, the original video was approximately 30 seconds. I was going to put it in here for comparison, but I figured most people wouldn't want to sit through that again. So if you do want to see it, there'll be timestamps in the bottom and you can just go find it. But otherwise you can just find the final edit. And I'm going to play it a couple times just so you can get a feel for it. So we can play this friend and then hit forward 2. Target player sacrifices an artifact. So we can play this friend and then hit forward 2. Target player sacrifices an artifact. So I think that looks pretty good. So let's recap what we've done. We took a 30-second, very painful to watch video, shortened it to around 5 seconds, preserved all the useful information, and managed to make it not feel like you're watching a robot. If you want some more extended examples, because it's hard to get this in like 30-second clips, I've linked to 2 pretty demonstrative examples from my actual gaming channel, because I have a backlog before I was editing my videos, and now I edit all of them. So you can compare the flow of both of them to get a true feel for how this works on a longer time scale. And with that, we're pretty much done. So to wrap things up, I'm just going to walk through a pseudocode implementation of what the full editing algorithm would look like. So here's our function edit video, and it takes in 2 channels. There's the video and audio signal. And the first step, we're just going chronologically through all the things we've talked about. So step 1 is find silence in the audio channel by looking either at the volume and seeing when it's above or below a threshold, or checking the spectrum and seeing if it matches something you're looking for by using the neural network or some other fancy method like that. The second step is detect a lack of motion in the video. And you can do this by either using the frame difference or optical flow algorithms that I showed before. So now you have your 2 mathematical representations of not audio and not video, because remember you're storing them as a list or an array of vectors. And now what you want to do is add padding to them. So either you take that list and shrink them on either side according to whatever padding value you've decided, or you can add padding to your audio and video signals before you find the silence and not moving parts. Both of those are quite equivalent, but you just need to do it at some point. The next step is to find the intersection of these padded audio and video, or padded silence and padded not moving video, to find when the video is quiet and not moving. And this will give you your array of cuts. And then the last step is to implement these cuts in software. So again, I used FFmpeg to automatically send a list of cuts and return a video. You can use whatever thing you want, but you just have to basically apply them both to the video and audio channels, and then recombine them to get your final edited video. And then that's it, you just return the edited video. So here's where I talk about the caveats. The first is that this was only a 0th order video editor, because we're representing them with a binary signal, but real video signals can't really be represented completely by using this. There's more complex nuances that we would miss with this approximation. For example, if you have a dramatic pause for effect, that would just be completely cut out by our editor. Or maybe you get some mixing between channels where on-screen actions are only important if they're accompanied by video signals. So you would be including stuff that you just don't need to. And I'm currently building an editor to take all these into account and also introduce the neural network spectrogram mapping that I talked about. So if you're interested in seeing that, it might be worth subscribing so you can see that video when it comes out. And additionally, this entire video and all the animations I wrote in it were entirely animated using JavaScript animations in a web browser. And I did all this with a custom automated animation library that I wrote. And in this case, the source code for this whole video was around 19,000 lines of code. And when I figure out how to get web hosting, I'll put it on the website. So check the description depending on when you watch this, and you might be able to just go play with the source code for this. But I got to figure out how to do that first. If you're interested in a video explaining how I made all these animations happen, please consider subscribing, and I'll be making that very soon as well. And then lastly, these videos do take a long time to create. And a great way to support me is by getting some of my art. So for example, this animation right now I made, it might not be available for sale immediately when this video goes live. So depending on when you watch this, check the description for my website where you can get some awesome metal prints for your house or whatever you need. Thank you guys so much for watching, and I'll see you soon.